number on the top, right? So it's the one that McMahon obtained, right? So it's you see here, it's interesting that the last 6 digits are the same, right? And the deviation comes over here in the 7th digit, right? So he's off by 1 million out of 3 trillion, right? So which is actually pretty good. So what happens is that so as we discussed, I think I told you, the formula for partitions does not exist. Like, so you cannot write the formula P of n equals explicit expression in terms of n, but as we know by now, there are various other things you can do. You can express P of n in terms of P of previous n's, right? And today we'll get another formula like that. Okay, so this is so in this case, turns out that the Ramanujan was not quite right, and so in fact about maybe 10% of what he did, so is not quite correct. But the rest is absolutely pure ingenuity, right? So a lot of fields in math, like a lot of results in mathematics, they originated from Ramanujan's ideas in 1920s. Yeah. So unfortunately, he did not live long because it was pre-antibiotic era, and he died. Yeah, so what is now is a simple preventable disease. So yes, and now the British professor will get astonished.
My God, you're close. 2%. Well, I'll be damned.
Yeah, I'll be damned. So yeah, so what we're gonna do today is we'll try to understand this formula, understand the derivation for the formula of P of n. So let's get back. Let's see where we ended last time. Over here. Okay. Any questions here? Yeah. So I see somebody said that there are no questions on the homework. Yeah, it's okay. So you can submit the homework. You can submit homework later. How to complete the assignment? What's the question, Ines? You have any? So you did not know how to code, or you did not know how to prove the formula?
Both. I didn't know how to code because I didn't know that like we needed to know how to code for this class.
Okay, that's fine. Okay, that's fine. It was just just in case you like it. So if not, you can just use Mathematica. Like do you have access to Mathematica?
No.
No. Oh, okay. So can the admins arrange that? Do others have access to Mathematica? I think Emily told me that she did. It's okay, don't worry. So it was just a fun exercise to see that how. So nice things about partitions is that you can actually write a simple code which do the calculation, but there's no like simple formula for it, right? And you can prove a bunch of those properties that say symmetric equals odd and distinct and so on, and you can derive the relation for P of n, but it's not as straightforward as it seems. So it's fine. So like I don't think it will be graded or anything. So just if you like to code, it's you can do it. So I think I gave this particular not the course of lectures, but just this one lecture about partitions at Berkeley, and then one of the students, he coded as I was speaking. So he coded and then he sent me P of 200 like in 10 seconds or something like that. Yeah, so it's some folks like to code more than others, so that's okay. Okay, but since you also said you had troubles with deriving this formula for P of n, right? So where is it? Okay, can somebody help? Can somebody explain how to prove that? Where do you have it? Here. So in fact, there are two numbers, right? So there's n3n minus 1 over 2 and n3n plus 1 over 2. Can somebody explain this? Who wants to, yeah. So n here is this index. Yeah, go ahead.
I can explain how I did it. So
Sure.
So mine was you take the pentagonal number and you split it into two numbers, like a triangle number and a square number, which is like kind of a rectangle.
Yeah, exactly. So do remember that we did this. That's why we did this exercise last time, right? So you see this table here. We have there are two types of pentagonal numbers. To say here, there's 12, right? And you can think of 12 as 9 plus 3, right? So if you draw it, right? So you have a square number and the triangular number like this, right? So you just add them together, right? So all for example, 35 is equal to 25 plus 10. So these are for positive integer indices, and then for negative indices, they just go on. Yes, we have 26, right, is equal to it's the same 16 plus 10. Right, so then for 3, so here, and for 3 we have 15 is equal to 9 plus 6. So the difference between, say, so this is P3, and then P minus 3 is that you take next square number, right? So, and then another one over here, so you can just draw it like this. Okay, I continue. So that's P minus 3. So we split the number into, okay.
Yeah, so you split it into two separate equations. And I split it into n times n plus 1 over 2 for triangular number, and n times n minus 1 for the square number.
Why n minus 1? Square is a square, so it has n by n.
Oh yeah,
I
was looking at the smaller of the pentagonal numbers. For the bigger one, it's just n squared.
What? Well, I think I see. I think what you're saying. Good. I think I understand what you're saying. So you said you just take this rectangle here. So for the negative for the pentagonal numbers with negative indices, you would take the rectangle. I see. So but then it should not call it a square number, right? Because it's not a square anymore. So the idea is that okay, I see where it's going, but let's just stick with the squares, right? So n. Okay, so this one, let's not do the rectangle. Let's still do the square. So here, in both cases, if you have square 3 by 3, right? So this is 3 by 3 square. So which is in this case is it S3, right? It's the third square number in both, right? And then in this case for P3, this is the second triangular number. And then here, well, actually, let's just stick with the minuses. This is S3, S minus 3, the symmetric. And here, this triangular number is T with index minus 4, right, which is equal to 6. And here, T2 is equal to 3, right? So let's write the formula for triangular numbers. So it's, as you said correctly, Tn, right, is equal to n times n plus 1 over 2. But now let's formally apply this to any n. So let's assume that n can be also negative, right? So we'll see where the minus 1 comes from. Now assume that n is negative here. So let's denote n is equal to minus m, right? And so what is it equal to? It's equal to minus m times minus m plus 1, or it's m times m minus 1 over 2, right? So that's where the minus 1 comes from. So it's like if you relabel negative indices to positive indices, that's where you get this minus 1. But like you can formally just keep it as is. So assuming here that n is a integer, any integer, not necessarily positive integer. Okay, and then you just add n squared. Okay, so and then you can simplify it, right? So you can multiply. So here we have n squared plus n plus 2n squared divided by 2. So it's equal to 3n plus 1 over 2. So here you do think of n as any integer. So again, n is in z, right? It's a positive integer. Excuse me, it's any integer, not necessarily positive. So if you do want to have a sort of special cases, you can say, okay, so If n is bigger than 0, then Pn is equal to 3n n plus 1 over 2. If n is less than 0, then we have Pn is equal to 3n, rather minus n. P minus n is equal to 3n and minus 1 over 2. So for example, yeah, that's right. So for example, P minus 3 is equal to 15. Okay, does that make sense? Is that did anybody do it any other way?
I think it's n times 3n plus 1 instead of the 3 being outside.
Oh yeah, thank you. Yes. Yeah, it's a typo. Yeah, so it's 3n plus, right? So it's 3n. I should have said sooner. Yeah.
I have a question.
Yeah,
What does S of n mean again?
it's the square number. Look at the table. So
Oh.
so yeah. So remember, like the first lesson we talked about those triangular numbers and square numbers. We had some pictures. So Sn, as you can see, is just the square of n. So it's 1, 4, 9, 16, 25, 36, right? So it's number of cells in an n by n table, right? Yeah.
I have another question.
Sure.
Oh, I'm sorry.
Yeah, go ahead.
Oh, why did you set n equal to negative m? Like, what was the purpose of that?
Oh, just to show that there are sort of two two series. There's a formula with m plus 1 and m minus 1. Right. So
Is there like a difference?
Yeah, so you see the pentagonal numbers are not symmetric. So for example, they're not symmetric with respect to reflection around 0. So see, you have, for example, P6 is equal to 51, but P minus 6 is equal to 57. So, and they're not precisely symmetric because of this kind of +1 thing. So if you, so see, this formula is not symmetric relative to reflection n to minus n. So, I mean, you don't have to do it. So this is the full answer, right? So if you like, so this is formula for Pn, where n is any integer. It is just, we label them as positive integers, right? It's just, natural numbers, we count them 0, 1, 2, 3, and so on. So if you sort of label using this n equals negative m, if you want to label the negative integers sort of like this, then there will be sort of two series of numbers, right? So which we call Pn and P minus n. I'm going to show you the picture again. Just give me 1 second. So that's what we did last class, right? See, so they go in pairs like this, right? So this is P1, P minus 1, right? P2, P minus 2, and so on. So and it's important, right? So they go in pairs, and then in that formula that some of you wrote in the homework, right? We're going to talk about a partition function today, the generating function for partitions. And then there's certain sign pattern between those terms that you see. So they go like plus plus minus minus plus plus minus minus in the Euler formula, and that's precisely why, because those pentagonal numbers, they also go in pairs. Emily, what's the question?
I have just one question. So I did the homework and I did the sum of 3 triangular numbers, was able to give me the pentagonal number. I did it like a different way.
Okay, I think what I'm saying is this, right? Let me try see if I understand. So let's look at this picture here. Like this, right? This, like that, right?
Yes.
Yeah, of course, yeah, absolutely. Right. And that comes back to what you can. Yeah, and then there are sort of a couple of ways you can do it, right? So, somebody mentioned rectangle before, right? So, yeah, so with rectangle, so it comes down to calculation of the sum, right? So So if you take two triangular numbers, so Tn, and then add it to itself, so twice Tn, right? You're gonna get n times n plus 1, right? So it's the rectangle, but you can do something different. You can say Tn plus T n minus 1, then what will you get? So let me draw them for you. Say here there's one, and then the other is like this, right? Are you gonna get a square or a rectangle? Okay, I remind you the formula for Tn is n minus plus 1 over 2.
You simplify that and you would just get n squared.
Of course, yeah, right. So what I just thought you can figure that from pictures. So see, it's right. So we have a pair of pentagonal numbers, right? In one of them you get to get the p negative one. So essentially, so p minus n is equal to 2tn plus tn minus 1. Is that right, Emily? That's for the negative one. And then p
Yes.
positive n is equal to and now here you add these, right? So here it will be equal to, you can check, it's equal to 2tn minus 1 plus tn. And if you add them together, let's do it. So this will be, well, 2n squared plus 2n, right? And then plus 2n. Cool. Yeah, so sorry, not enough space here, but yeah, so you can check, you can check that it works, right? So let's do it. So if I'm going to move, something happened. Okay. So I'm continuing. So it's 2 n plus 1 over 2 plus n minus 1 and minus 2 over 2. You can simplify this, right? And then you'll get the formula, right? One with n 3 n plus 1. So you get you get this formula for all for all. Actually, I think I made a typo on the previous slide. So yeah, so Pn. Okay, let's calculate it, right? So it's equal to what? The big 2 here, right? And now it's
Shouldn't that
Yeah.
second quantity be n minus 1 times n over 2 and not n minus 1 times n minus 2?
oh yeah, thank you. That's right. It goes with the plus. Yeah, I see something is wrong. Yeah, so it's n. Yeah. I'm still in my morning. And yes, n minus 1 n. That's right. Minus 1. Yeah. So if you simplify it, you're gonna get 2n squared plus 2, and then plus n squared plus 2n. Yes, plus n squared minus n. Right. So that's equal to 3n squared plus n over 2. Right. And if you do this one, you'll get 2n minus 1 plus n squared plus n divided by 2, which will give you 3n squared minus n over 2. Exactly. So if you want to keep this, so to get this formula, it's equal to 3, and again, n times 3n minus 1 over 2 for any n. So n is in integers. Okay, good. So see, yeah, it's a good exercise. Yeah. or if you like, you can prove it by induction. It's like look at the pattern and then sort of make an inductive assumption and make inductive step, right? To show by induction the formula works. Other questions? Okay, so I'm glad that we recall. Yeah, go ahead.
Oh, okay. So, the way that like this method is like split up is into 3 triangles, right?
Yeah. So, but they are not of equal size. So over here, there are 2 triangles of this size, of size n, and 1 triangle of size n minus 1, because it's a smaller cap over here. Like, and then here, I'm sorry, yes. So this is n minus 1, and then this partition, you take 2 triangles of smaller size, which sort of oriented like this, right? And 1 triangle of a bigger size. Yeah. And as you can see, they differ by n, right? So if you delete the bottom row, you'll get the previous one.
I see.
Yeah.
And just to clarify, n is the number of squares in the triangle.
Sorry, second numbers. Number square. Yeah. So you just count. Yeah, you count number of squares. That will be the corresponding triangular number. Yeah.
Okay.
Yeah. Right. So of course you can write everything with formula, but also with pictures, it's more sort of direct. In fact, we'll prove a theorem today. If you open a book, the proof is a bit messy with formula, but with pictures, it's pretty much straightforward. Okay, good. Other questions? Okay, great. So these are pentagonal numbers, and we will need them, right? So let me remind you what we did with those guys last time. Yeah, we'll talk about this theorem. So we talked about 2 kinds of partitions, which are very specific, right? So first of all, it needs to be a distinct partition, right? So no 2 parts are the same. And then you count how many parts this partition had. And there, of course, we can have every number is either even or odd. So there could be distinct partitions with odd number of parts and distinct partitions with even number of parts. So we'll, excuse me. Can you hear me? Yeah, I think I just touched my microphone. Right. So, and then we looked at, and then for most cases, most of the time, these numbers, they match each other, right? So not for 8 is the same, for 9 is the same, 10 is the same, 11 is the same, but and then this is the matching correspondence. So can somebody summarize how the matching goes? So what's the rule here? So I think last time we did not kind of completely summarize it, but we'll need the rule now, right? Because we're going to prove a theorem. So what is the dictionary? So how we make the correspondence between these kind of partitions?
You just kind of like take the block at the end of the like larger part and then like add it back to the first column.
What if there are 2 blocks like here?
You try and like choose like the part with 1 block, but if there are 2 blocks, then like in that top right situation, you add 1 block to like the first column and then another block to the second column.
Mm-hmm. Good. So you would right. So you need to here right. Although here what we did, we took this block and put it up here, right? Okay, right. So and then okay. So yeah, it's essentially we'll look at the right. So in this case, you have blocks sticking out here, and there's a block over there, and then so in this case, we decide, yeah, we take this block on the bottom and put it put it up here. Okay, but let's go a little bit higher. So, but okay, so maybe we need to make it a little bit more precise in a second. But okay, and now, but at any rate, for n equals 12, for example, the numbers of those partitions are different. So we have 8 partitions with odd number of parts, and then 7 partitions with even number of parts. And this partition, which looks like a pentagon, which we draw it, does not, it falls out from the correspondence from the dictionary. Okay. So yeah, that's what we just revised. Pentagonal numbers, they have this very nice properties. So this is what we're going to prove today. So I'm going to show you the theorem once, and then we'll prove it like in maybe 10 minutes. So if n is not a pentagonal number, then the number of even distinct partitions of n, let's call it QE of n, equals the number of odd distinct partitions of n, call it QO of n. And so the total number of distinct partitions of n, call it Q of n, is, well, it's the sum of even and odd. So in this case, it's twice, say, Q odd, which is even, because it's a multiple of 2. Now, if n is a pentagonal number, say P sub j, then the following formula is true, that QE is equal to QO plus minus 1 to the power of j. So it goes as a plus and minus. So in this case, Qn, the total number of those distinct partitions, is equal to twice QO of n plus negative 1 to the power of j, which is odd. So the total number of distinct partitions is odd when n is a pentagonal number. And here there are 2 examples, right? So for n equals 5, right, we have seeds. So there's a column here, and there's a hook, which sort of correspond to each other by moving blocks, right? And then this is a pentagonal number, and then this is the same thing for 7. So for 5 and for 7, see, like the excess is always on one side, right? So there's always one more even partition, like the partition with even number of parts. Okay. So this is what we want to prove today. Now let's see how the where we are going with this. So we want to derive. I remind you the formula for not the formula. We want to try to understand P of n, the number of partitions, and so did Leonhard Euler, back in 18th century, right? So and Euler, so Euler was really a great genius, right? So like if you would try to compare him with other mathematicians, he really stands out like in a category of his own, right? So so he had published like a lot of papers, I think around 400 papers when he was alive, and then another 400 was published after he died, right? So like to put it in perspective, like right now, like with computers and everything, like by the end of his or her career, mathematician publishes maybe 150, 200 papers. So like he's probably one of the most prolific scientists of all times, and yet he had trouble with understanding those partitions. So what he'll do, he'll just try to multiply these numbers, right? This expression, say 1 minus z times 1 minus z squared. So think of z as a formal variable, because you know how to multiply. So you would do this, you get 1 minus z squared plus z cubed. And I think some of you did this in the homework, so I'm glad that you looked ahead. And now you do 3 of them: 1 minus z squared, 1 minus z cubed. It's a bit longer, but you get this expression: 1 minus z squared plus z to the 4th plus z to the 5th minus z to the 6th. So far nothing special, right? So you have all powers here. And then he said, okay, what about if I consider this infinite product? So I'm going to keep multiplying all the way to infinity, right? So if you know calculus, then you probably get, at least have some idea of what calculus does. This expression might not make sense, right? Because say if z is large or negative and large, the product will diverge, right? You multiply a number by a bigger number, by a bigger number, by a bigger number, you're going to get infinity. So for this to make sense, z needs to be small, right? So like if z is a complex number, its absolute value should be less than 1. So that this product will diverge. Basically, the idea of the convergence of infinite products is that the expression that you're multiplying should eventually approach 1. Right, and it does, right? Because when you take a number which is smaller than 1 and square it and cube it and so on, the number will get smaller and smaller and smaller and smaller. And then you can multiply 1 by itself as many times as you like, and the product will still make sense. Right, so this is this Euler function phi of z. We're going to work a lot with this. Okay, and then, well, Euler, he sat and then he calculated phi1, phi2, phi3, etc. And then he found something interesting. So he found that some of the coefficients in front of some powers, they just drop out. Starting from phi to the 4, there is no coefficient in front of x cubed or z, I think I relabeled here, or x to the 4th, and then there's no coefficient. And then you can see there's the relative holes in this lattice, right? The many coefficients are missing. And then, well, which numbers stay the same? Which numbers stay? So it's 1, 2, 5, 7, right? So those are already pentagonal numbers that we saw. And then, but at the moment he did not know it, and so this is what he wrote. He said that, that's what Euler wrote himself about his identity. In considering the partitions of numbers, I examined a long time ago this expression here, in which the product is assumed to be infinite. In order to see what kind of series will result, I multiplied actually a great number of factors and found, well, this, right? So see, you have 1, 2, 5, 7, 12, 15, 22, 26, 35, 35, 40. So those are our new best friends. So the exponents of x are the same, which enter into the above formula. Also, the signs plus and minus arise twice in succession. So they go plus, plus, minus, minus. It suffices to undertake this multiplication and to continue it as far as it is deemed proper to become convinced, see how people wrote back then, of the truth of this series. I have no other evidence of this except for long induction, which I have carried out so far, and that I cannot in any way doubt the law governing the formation of these terms in their exponents. So he still did not have an idea. I have long searched in vain for the rigorous demonstration of the equations between the series and the above infinite product, and I proposed the same question to some of my friends with whose ability in these matters I am familiar, but all have agreed with me on the truth of this transformation of the product into a series without being able to unearth any clue of a demonstration. So it was still a mystery back in 1700s, but it was figured out. People figured it out a bit later. So let's do it right now. Any questions so far? I just one. Good. So take this function 5z. So let's prove that the only powers that remain are those pentagonal numbers. And the proof, as always, so this will be like the core theorem of this. Like this is true, means that we understand this formula for partition. Yeah. So these are our best friends, and now we need to prove that this is the case. So here, if you want to write like the general formula to look like this. So you remember we just talked about, so there are two types of pentagonal numbers. So this will be Pn. So they go in a series, right? So this is Pn, and this is P minus n. So they always go in pairs, or if you want to like them as a, so here the sum goes from over positive integers, over natural numbers, and here the sum goes over all integers, right? Okay. So let's try to prove this. So a claim is that the coefficient in front of Zn here in this formula is equal to the sort of, if you formulate it in terms of partitions, is the number of distinct even partitions of n minus the number of distinct or odd partitions of n, right? And if you remember my comment previously, these two, they go in pairs, right? So this number is equal to, this difference is equal to +1 2 times in a row, and then -1 2 times in a row. And it goes in this pattern, plus, plus, minus, minus, plus, plus, minus, minus, and so on. Okay, so this is the theorem again, right? So if n is not a pentagonal number, then we have the number of even partitions, even distinct partitions matches the number of odd distinct partitions. And if it's a pentagonal number, then the formula is QE is equal to QO of n plus -1 to the j. So this is true, which is odd. Okay. So again, this is the matching of the two types of partitions that we saw before. But how about we take a bigger number. So like see in those, when the number is small, then the number of blocks in the rightmost column is actually also small, right? So here we can maybe take one block, put it upstairs, take one block here, put it upstairs. But when n is say 25, you have a partition like this, right? You have partition with 5 parts, right? And partition with 4 parts. So we need to kind of generalize our rule a little bit, right? I'm sorry. Yeah, so this is what we're gonna do. We're gonna take the we'll compare the following things. So we'll look at the rightmost column, and we looked at this. So we looked at this diagonal over here, the topmost diagonal. So those squares that they line up on a diagonal on top, right? So why do we need a diagonal? Well, because our partitions have to be distinct, right? So we're not allowed to have like a flat part. We're not allowed to have 2 parts equal. So either we have a diagonal like this, or we have, say, one of the columns is taller than the others. And in this case, for example, here, the diagonal consists just of one element, right? So here the length of this diagonal is equal to 1. In this partition, so in all and here the length of the diagonal is equal to 3. Right, and here, actually, I think this is also a good example on the top right. So see here, so the diagonal has 3 elements, right? And the column here, it has 2 elements. And so diagonal, so let's call it just D is equal to 3, and C for column is equal to 2, right? So we need to figure out, so and what we did here, we decided to take those 2 blocks and put one here and put one there, right? So yeah, so we could have done otherwise. We could have put this diagonal down, but then we would violate the partition rule, right? So then because there are 3 of them, we cannot put them all down. Or even if there are 2 of them here, we cannot put them all down, because then we'll have two equal parts. So the rule is, in a sense, it's more natural. So we need to preserve the property of the partition, right? So we need to make sure that it's kept distinct at all times. So this is what we're gonna do. Here's the rule. If the number of blocks in the rightmost column is greater or equal than the number of blocks in the topmost diagonal, as is in case here, greater or equal. So there are 3. So there are 3 of them here. So if you look at the right partition, so here the diagonal has. No, I'm sorry. Let's read. The number of blocks in the rightmost column is greater or equal than the number of blocks in the topmost diagonal. Then we move them from that column to the top diagonal, and otherwise we move the top diagonal to the rightmost column. Right. So and as you can see, it can always be done. It can always be done in the for any of the partitions, unless it's a pentagonal number, right? So here, see, the diagonal is 2. The in this case, the diagonal has 2, and then the column is 1. So this is 2 and 1, right? So well, I think so. Then put it here. Actually, did I make a typo? One sec, given I might have. Let me check. So it says, no, if the number of blocks in the rightmost column is greater or equal, no, smaller or equal, excuse me. It's smaller or equal, yeah. Otherwise, it's not going to work. Yeah, so because that's what we're doing. And then, yeah, so for example, here, you would take. So one block here, we move it up, right? So in here we have 2 blocks here, and 3 blocks on diagonal, we move it up, right? So if the rightmost diagonal contains less blocks than the rightmost column contains less number of blocks than the diagonal, then we move it up in the prescribed fashion. Okay. However, it's not always possible, as you understand now. So the problem appears with pentagonal numbers here. So for example, P4 is equal to 22. So here we have 4 and 4, right? And with so you cannot do anything. And with P minus 4, we have 4 and 5, right? So this procedure, this operation does not apply. It does not work. So you cannot apply this dictionary, right? So you can try to do something else, but then you would mess with other partitions, right? So then the correspondence will be not one-to-one, right? And then yeah, so and then because this kind of these partitions that go in pairs, right? So partitions with say P4, there are two of them, P4 and P minus 4, and in the same is true for every n, right? Then the following, and then see some of the partitions go with you have even number of parts, some partitions have odd number of parts. So with 4, we have 2 partitions with 4 parts, right? So they will correspond with sign plus, right? So there are the QE of n is equal to QO of n plus 1. Any questions so far? Yeah, so and this proves the theorem. Yeah, so unless we have a pentagonal number, unless n is a pentagonal number, the number of the number of partitions with even number of parts is equal to the number of partitions with the odd number of parts. And if it's a pentagonal number, then we need to look at the exceptions, right? So then there is a yeah. Okay. Good. So that's the that's the sort of essential part of the proof. And then now let's see how it can help us to understand the formula for partitions. So okay, so what we have proven, what this allows us to prove is okay. And now can somebody explain? So if this is the case, can somebody explain then why this formula is true? So why this product here will be equal to this expression? So what does this have to do? What do these partitions have to do with this expression here? So when we do this calculation, what do you do, right? You open the parentheses and then you combine terms in front of the same power of z.
So what I did when I was proving it for homework, I did each one individually. So you're doing z to the k. So it would be 1 minus z times 1 minus z squared times 1 minus z cubed times 1 minus z to the 4th. And then once you simplify all of that, you'll see that the numbers start changing into all the pentagonal numbers. So the exponents.
Yeah, so but this is the observation. Now, so we want to prove this, right? So what about if you go to 1 million, right? So the theorem is that you only have exponents with pentagonal numbers remaining and everything else cancels out. So I'm asking, yeah, so this was the observation. So and now we need to do the proof, right? So we just prove this theorem that this is how the pentagonal numbers work, right? So if n is not a pentagonal number, then you have equal number of even partitions and odd distinct partitions, right? And if it's a pentagonal number, then there's this formula. So what does it have to do with this expression? Yeah, so Emily, what you did is correct. We just need to explain why do you have those cancellations. So is there any connection between these cancellations and this expression here, that QE is equal to QO? So let's look at the expression a bit more carefully. So we have minus here, right? So so what do powers of z represent here? So when you collect coefficients in front of powers, each power of z, what do you have? Like, what does this coefficient represent?
There is no coefficient in front of z. It would just be a 1. There's only exponents.
Well, I mean, like, I mean, for any power, right? So, like, you would,
okay.
you know, yeah, it's a question in principle. So, do you see how to find connection between those coefficients and that formula? Also, notice that all the coefficients are either +1 or -1. There are no 2s, there are no 5s, there are no 7s. What's the reason for that?
Well, I was just thinking with like all of the like for instance with 3, 4, 6, 8, the non-pentagonal numbers, like you're basically trying to find ways of splitting them up into parts. Like for instance, with 3, it can either be 3 and 0 or 2 and 1.
Mm-hmm.
And the number of actual like parts it has is whether it's odd or even, which manifests itself in this equation as either being plus z cubed or minus z cubed.
Excellent.
Which means that
Precisely.
for non-pentagonal numbers, the two are equal and thus they cancel out.
Absolutely. So see, whenever you collect coefficients in front of each power, say z cube, as saying, or maybe z to the k for any k, so we're collecting these to my Zoom froze. Okay, I'm going to annotate here. The so say how you can get, for example, z cube, right? So z cube is either z cube multiplied by z to the power 0, right? Or z cube is equal to no, that's painful to do. Where's my, okay, I'm gonna have to quit it and start again. Or it's, you know, z squared times z to the first power, right? Or yeah, so in this case, there are just two. So z to the 0 is nothing, right? So 0 is no part. So here it's as if, so here, so z cube goes with a, so this is odd, right? It's an odd, you represent 3 as a column, right? And 2 plus 1, you represent it as this hook. So this has one part, this has two parts. And if you do the calculation here, you can see that z, when you multiply 1 times z cube, it goes with a minus sign. So you have negative z cube. And if you multiply negative z with negative z squared, it gives you plus z cube. And they cancel. So with the partition of 3, there are only 2 distinct partitions, right? One of them with an odd number of parts, one of them with even number of parts. And in this expression, they enter with the opposite signs. So they cancel out. And you can check that this is the case for with every other partition, right? So, for example, let's maybe do 5 or whatever. So, okay, well, what is the first? Yeah, we can try to do we can try to do 5. So. I got my annotation back. So what you can do is in front of z to the 5, right? So z to the 5 is equal to either z to the 5 times 1, then it's equal to z to the 4 times z. So what are the partitions of 5, right? We can remember them all. Or is equal to z cube z squared. What is that it, right? So all others will not be distinct. And actually, so the way we make sure that the partitions are distinct is because all those powers of z's are different, right? So here we have z to the first power, z to the second power, z to z cubed, z fourth, etc., etc. So if you had, say, two powers of z of the same, so two terms with z in the same power, then we would have had, non-distinct partitions, but this is not the case. Okay, so there are three of them. And now we can draw it. So 5. So the one, so this is a column, and then there's 4, 1. And then there's 3, 2. And this is our first pentagonal number. It's P5. Yes, it's P5. Excuse me, it's P2. I apologize. Yeah, P2 is equal to 5. P minus 2 is equal to 7. Yeah. So this is P1, P minus 1, P2, P minus 2, and so on. Does that make sense? Yeah. So see, it's a very smart way to encode all the distinct partitions just by counting coefficients in front of this z to every power. Yeah. So this phi, it would generate those, and what we have proven is that we will always have a cancellation. So the number of these partitions will always be the same, unless n is a pentagonal number, like in the case of 5. Yeah. Good. So that's the first part of the construction of the proof. Now we're actually going to go to derive P of n, the generating function for P of n. Okay, so one of the homework problems will be to write this for the generating functions for distinct partitions, but I'll give you the homework later. Okay, so moving on. Good, so we know that phi of z generates those pentagonal numbers, and the coefficients go minus, minus, plus, plus, minus, minus, plus, plus. Why? Well, because that's how pentagonal numbers go, right? So for every pentagonal number, there is Pn, and then there's P minus n. Okay. Now, what we're going to do now is something fun. So we want to do divide by this phi of x. So denote the new function P of z, which is 1 over phi of z. And again, think of it as a formal expression. So if you are sort of prepared on calculus, again, think of z as a small number, right? Whose absolute value is smaller than 1, then this expression makes sense. Okay, so now let's try to understand this a bit better. So you probably know this formula that 1 over 1 minus z is equal to this infinite sum. Can somebody remind us why this is the case? How can we prove this formula? And then, so assuming that z is small, right? Assuming that absolute value of z is less than 1. Can you prove this equation, this identity?
This is like a geometric series.
Absolutely, yeah. This is a geometric series, right? So
Common ratio of z. So you just sum it up, and
of course, yeah. So this is just a geometric series. So if you like, there's another way to prove it. You write 1 minus z to some power n, right? And then you can prove that this is equal to this formula, right? Plus z squared plus z to the n minus 1, right? Why is this true? What happens if you open up the parentheses and start calculating?
Some of the numbers get like canceled out.
Yeah, exactly. In fact, all of them except the first one and the last one, right? Yeah, so all of them will cancel except 1 and minus z to the n. Yeah, and then you can divide by 1 over z, right? So you'll have 1 minus z to the n divided by 1 minus z is equal to sum z to the k. K goes from 0 to n minus 1, and then you take the limit and goes to infinity, right? and assuming that z is small, absolutely is smaller than 0, then z to the n goes to 0, right? And that's how you get this one. Good. So it's part of the construction. And now, if z is small, you can also do this, right? You can also say that if 1 over 1 is z is equal to this geometric sum, then 1 over minus z to the k is equal to this sum. And you just replace z to the k with a different letter, and it's literally true. Okay, so and now, well, let's do this for every every parenthesis. So it's like it's this, and then the right. So it's equal to right. So this is the problem. Now we're going to do this for every one. So 1 over 1 minus z is equal to this expression. 1 over 1 minus z squared is equal to this expression, and so on and so forth, right? So you would get this kind of product to have infinitely many infinite sums. So it's the product of infinitely many infinite sums in a denominator. It sounds pretty scary, but let's try to kind of to see. Okay, so here they're in the denominator, but now using this formula, we can actually bring this to the numerator. So once we've done this, we can write P of z as this formula. So it's an infinite product, right? Because we have infinitely many parentheses of this infinite geometric sum. Okay. See if you agree. You don't have to take notes, right? A file is shared, right? So let's just make sure we understand it. Okay. So that's the some formal rewriting of the same function. So far we haven't done much. We just wrote it in a more convenient way. Okay. So that's the formula again. And now we're doing the same thing. We'll collect terms in front of each power of z. And let's try to understand what this coefficient represents. So each term is in this product will look like this. So say, well, we just take, say, one z from here, one term from the first parentheses, one term from the second, one term from the third, and so on and so forth. And then, of course, there'll be for every power, say n, each term in front of z to the n, for every finite n, there'll be finitely many monomials, right? Because you can only multiply to the n. Product is infinite, but when you truncate it to z to the n, we'll only have that many. So you'll have an expression like this, which looks like z to the k plus 1 plus 2k2, 3k3, etc., where k1, k2, k3, and etc. km are just some integers, right? Such that the sum is equal to n, right? Such that so we want to count the number of such products in this expression with this condition satisfied. So that's what it means to collect all the terms in front of the same power of z to the n. Okay, so that's what it looks like. And now let's see what it actually represents. So let's rewrite it like this. We have k1, which is 1 plus 1 plus 1 k1 times. Then 2k2 is 2 plus 2 plus 2 k2 times, etc., which is nothing but the number of partitions of n, right? With this many parts and with these columns. So you would have a Young diagram, right, with the km columns of height m, then k sub minus m columns with height m minus 1, and so on and so forth. So by construction, the coefficient in front of z to the n is P of n. So this is the answer. So let's do an example. It should look a bit too overwhelming. So take partition of 20, the 6, 6, 4, 3, 2, 1. So that's the Young diagram for this partition, right? Now, in terms of the previous formula, in sort of previous exercise, m is equal to 6, right? So that's the kind of the height of the topmost of the tallest column. Now k6, so the multiplicity. So k's are multiplicities, right? So they show us the how many times this partition appears, right? So if 6 is the height of the topmost column, then the km is equal to 6. So there are 6 of them. right? So k is a multiplicity. In this case, k6 is equal to 2, k5 is equal to 0 because there's no column, there's no part with 5 in it. Then k4 is equal to 1, k3 is equal to 1, then k2 is equal to 0 because there is no part with 2 blocks, and k1 is equal to 1. Right, so that's one of many partitions of 20 which will appear in that expression. Yeah, and then, well, that's so this is what you get. Any questions about the derivation? Yeah. So this is the P of Z is the generating function for all partitions. Yeah. So as you can see, it's much quicker. So you just need to calculate the coefficient in front of Z to the n in order to get P of n. Yeah. So okay. So yeah, we have a little bit more time now. Let's try to prove there's a formula that I mentioned. There's a recurrent relation which allows you to express P of n in terms of smaller P of n's. Now, by construction, this product is equal to 1, right? Because P of x is equal to 1 over 5x. So 5x here is this formula with the pentagonal numbers, right? And P of x, we'll just write it in general form with a generic form with those coefficients over here. Okay, so, and then, well, let's try to calculate right now with several first non-trivial coefficients in front of x and try to deduce relationships between P of n's. So can we calculate, so first non-trivial coefficients between, so what will be the first non-trivial power here? So it will be power x squared, right? X to the 5, it will be x to the 4 also, right? So x to the 4 and so on. So this has to be equal to 1, meaning that all coefficients in front of x's have to vanish, right? Because the right-hand side does not depend on x, the left-hand side depends on x, which means that every coefficient in front of every power of x must be 0. So take a look right now and tell me what are the relations, like what are the conditions which needs to be satisfied for this to happen. Let's get several few. Was the question clear? Okay, let's do one together. So like in terms of x, you get what, well, with x is pretty useless, right? So you have what, -1 plus p of 1, right? And for x squared, we have what, -1 minus p of 1 plus p2, right? So from here you get that p1 is equal to p of 1 is equal to 1, and that p of 2 is equal to 1 plus p of 1, p of 1 which is equal to 2. Let's do a couple of more. So we're doing a very simple thing. We just multiplying one parenthesis by another and then collecting terms in front of the same power of x. So the next power is 4, I believe, right? And then, yeah, so it will be also p4 x to the 4, and p5 x to the 5. somebody please say something. What's going on? Is it not clear or?
How are we supposed to do x to the fourth if we don't have an x cubed?
Well,
Oh, well, we have a p. Never mind. Never mind. Okay, 1 second.
sure. They have this guy over here, right? Just collect everything that appears in front of x to the fourth. If you like, you can annotate whenever ready, or you can say it to me or paste in chat.
Is it just P of 4 minus P of 3 minus P of 2?
Yeah, of course. Okay, so P of 4 minus P of 3 minus P of 2. And remember, we talked about till 4, it looks like Fibonacci numbers, right? So this must be 0, which means that P of 4 is equal to P of 3 plus P of 2, right? Which is equal to, well, and then you need to calculate P of 3, those also x cubed. I see. I forgot to do x cubed, right? So, but yeah, well, let's do also x cubed. So with x cubed, we'll get what? P of 3 from here, right? And then minus P of 1 minus P of 2, right? So, so P of 3 is equal to 3, right? And then P of 4 is equal to 5. And, you know, at this step, the Fibonacci pattern drops, right? Because when you calculate coefficient in front of x to the 5, right? Then you'll have, it will be different. It will break down, right? So let's do x to the 5. So we have what? P of 5, right? That comes from this term. And then what? We have to sort of, yes, minus P of 4, right? Minus P of 3. So this is so good because of these two minuses. Minus P of 3, and then what else can we do with the 5? We can take, there's also 5 here and then 1 here, right? So plus 1. And that's plus 1 breaks down the pattern, right? Because so from here we have that P of 5 is equal to P of 4 plus P of 3 minus 1. And instead of 8, as if it was the case with Fibonacci numbers, we get 7. Okay. Yeah. And so on. Again, you can teach your computer to do it if you like. So these you'll generate well, infinitely many recurrent relations for Fibonacci numbers. They'll look like this, right? There's a certain triangular structure here. Okay, good. Now, yeah, so Euler eventually figured it out, although it took him a lot of time. Yeah, so and sort of you get those numbers and see that the oh yeah, so what is more important? Yeah, so if you keep doing this, right? So because of the structure of this expression, right? So here we only have terms that whose powers are pentagonal numbers. So the way this expression looks like is the following. So you take the recursive relations works like this. You take so P of n is equal to the following. So you take P of in the right hand side you have a sum, right? Well, rather linear combination with the pluses and minuses in the same pattern. Plus plus minus minus plus plus minus minus of P of n minus the pentagonal number, right? And the sign pattern is the same, right? Because so here P of n is equal to P of n minus 1 plus P of n minus 2. So these are the first two pentagonal numbers, right? It's P1, P minus 1. So they go with a plus. Then there are two numbers P2, P minus 2. They contribute with minus. I mean, by minus, I mean these signs, which contribute to the formula, and so on, right? So P3, P negative 3, they contribute with the plus, and then P4, P minus 4 contribute with the minus, and so on. Now, for every finite n, as you can see, this sum will truncate, right? Because we do not define p of negative integers, right? So p only makes sense of 1. We can, if you like, you can define p of 0 is equal to 1 just for consistency, right? So if you do that, you'll see that this formula always is, for every n, the formula is always finite. You only need to take into account finitely many terms before. Okay. Questions? Right. So, and then if you do that, you can draw a really cool picture here. I call it Euler's ruler. So I know the picture might be a bit overwhelming, but what it does is essentially does this plus minus plus pattern. So you can think of it as a ruler, which you can apply to the list of numbers. So here we have what's it, 1, 2, 5, 7, 12, 15, and so on. So we have those pluses and minuses on the corresponding places with the pentagonal numbers, and then you just make a list. So say here you just make a list of p's of n for all n in the decreasing order. So say here you have p of 7, p of 6, p of 5, etc. And then you just take this ruler and then you kind of apply it on the left, on the right, and it will tell you what you need to do, right? So to get 22, you do 15 plus 11, right? It's, what is it, 26 minus 3 minus 1, 22. Or here, 15 is equal to 11 plus 7 is 18, minus 2 minus 1 is equal to 15, and so forth. Yeah. So this is also another way to understand the formula for P of n. Good. Okay, so let me explain your homework for next week. So this time I think I can give you a little bit more work. So it's okay if you didn't finish it. So we'll discuss it next class. It's like appetizer for the next class. So remember, we talked about distinct and odd partitions, and we have shown that well, here the number of odd partitions of n matches the number of distinct partitions of n. So first problem will be to write down this generating function for those, say, for distinct partitions. So write an analogous function. We can call it f of z or f of x, which would only count distinct partitions, and find this another function, say fd, and then another function f o, which would count odd partitions. So, well, having known what we learned, what we did today about this, well, generating functions, try to come up with your own function for distinct partitions and your own functions for odd partitions. So it will be some infinite sum or infinite product, whichever way you like. And then using those functions, prove the theorem that odd equals distinct. So remember, in the first lesson, we did it by moving some blocks, doing this binary representation and stuff. But now let's do it using partition functions. Okay, so that's the first problem. And we have time, we can actually probably start doing this one. Actually, yeah, not that. And then there are two more problems. So first equation, so it's not directly related to partitions, but it's the method with which we prove it is very close to what we did with the partition functions. So here we have an infinite sum. 1 over n is an integer to the power of s, and s is a prime number. So sum of I goes from n goes I to infinity. N to the s is equal to, so I think there's a typo here. It must be, yeah, it should be what it should be from 1 to infinity. Yeah, so it should, sorry, n to the, okay, I'll send you the correct formulas. Yeah, so